Good morning, good afternoon, good evening, wherever you're joining us from. I'm Ira Feldman. I'm the MEPTEC Executive Director. I'd like to welcome you to today's MEPTEC IMAPS Semiconductor Industry Speaker Series. The next presentations in the series will be on March 10th with John Park from Cadence Design Systems, talking about the difference between heterogeneous integration and system and package from an EDA perspective. And then on March 24th, Tom Green from TJ Green Associates will talk about moisture control in Class 3 medical implants, and especially in terms of hermeticity and other packaging challenges. And this is just a reminder to support MEPTEC. MEPTEC is a membership-based supported organization, both from individual memberships and corporate memberships. Please contact Betty Cooper, bcooper@meptec.org for more information. But this is the support that makes free events like today's Semiconductor Industry Speaker Series possible. So please take a moment and help support MEPTEC. For today's Semiconductor Industry Speaker Series, it is my pleasure to introduce Bharath Muthiah and Ravi Agarwal from Facebook, who will talk about system-level optimization for data center application. Ravi has over 16 years of experience in high-tech advanced packaging, supply chain, product management, and operations. He is the technical sourcing manager at Facebook Infrastructure Group, and he's responsible for driving advanced packaging for both networking and artificial intelligent machine learning compute applications. He is also driving the chiplet business workstream in the Open Domain Specific Architecture ODSA subproject within Open Compute Project OCP to enable the chiplet marketplace. He has a PhD dual major in material science and engineering and polymer science from North Carolina State University and an MBA from University of California, Berkeley. So, first Ravi will speak, and then we will hear from Bharath Muthiah. He's the technical lead in the Facebook infrastructure team for servers and AI platform sourcing, and he works with partners to increase the efficiency of solutions for Facebook workloads. And he's been actively involved in standardizing platform disaggregation and interoperable solutions for future server and AI platforms. And he has over 15 years of experience in multiple generations of data center processors and solutions, in particular working at Intel on cloud, enterprise, and high performance computing and network infrastructure markets. So I'm very happy to welcome both speakers. We will take some breaks during the presentation to answer any questions you may have. So please use the Q&A tool. Go ahead and ask your questions as the presentation goes, and I'll ask them at an appropriate time. Also, we will make the slides and the recording available early next week. You'll get some email letting you know that they're available, but they'll be posted on the meptec.org website and on our YouTube channel, youtube.com/MEPTECpresents. So with that, I would like to turn it over to Ravi.
Thanks, Ira, and thanks, MEPTEC, for giving this opportunity. Today, me and my colleague Bharath will be talking about system-level optimization for data center application. So the agenda for today's talk is we'll discuss about Facebook scale, AI ML application, and then we'll be talking about some of the challenges we are seeing in network power, and followed by some of the chiplet work which Facebook is driving in the ODSA domain. So Facebook is now a combination of many platforms. Some of them are more well-known, such as Instagram, WhatsApp, and Facebook. And some of them are less known, such as Workplace, which is B2B communication tool, as well as now we have Oculus. Facebook has over 2.7 billion monthly active users, and this is the biggest social network platform worldwide. And people are using them every day, and what they share is changing with the time. And what we are learning is the type of content being shared is becoming richer and richer, and with 10 billions of messages being sent across our platform and billions of video calls or live broadcasts. And AI ML is becoming an increasing part of our workload. As you can see, about 50% of our workload is feeding through ML workload. Facebook now owns about 15 massive data center. Each of the data center has about 5 to 6 DC per site that span across US, Europe, and Asia. Our data centers are contracted for 100% renewable energy and are 80% water efficient than the average data center from other hyperscaler. Now, I would like to hand over to my colleague Bharath, who will discuss AI and ML applications. Bharath.
Thank you, Ravi. So through the next 20 minutes or so, I'll talk through a couple of things. So first, I'll talk about the types of applications and their growth CAGR that is driving the demand for innovation in the packaging and test space. And then second, I will get into discussing how at Facebook we've approached things from a system level, from a rack level, form factor level. So that may be something that is not very apparent to the packaging and test community. So I would like to kind of share that. So that's helpful to the packaging and test community in terms of figuring out how we co-innovate together for future technologies and platform solutions. So those are the two things I'll be focusing on for the next 20 minutes or so. So this slide kind of talks through the different types of things at Facebook we need to do in terms of dealing with the ML AI solution space, right? So if you look at the box at the top, it kind of talks through the first section deals with the storage ingestion around getting data that we need to process and the huge amounts of data that need to be fed into the AI and ML computation domain. The middle piece talks about AI ML based training. Here is where we need the large accelerators which are getting pretty close to vertical and growing in size for the AI ML training space. And then the last section deals with AI inference, which is around running the trained models to deliver recommendations based on the trained models with real-time input. In terms of, if you can just go back to the earlier slide, Ravi. In terms of the growth itself, as you can see, these numbers are showing the 2018 to 2019 growth numbers. So as you can see, the growth is pretty significant and in many of these cases exponential. The data that we are serving is growing 3x. This was 2018-19, but you can extrapolate it into similar trends for now and in the future. And similarly, the types of training and model growth also continues to grow at a significant rate. And the amount of inferencing that we need to do also grows at a fairly significant rate into the trillions of predictions and the billions of translations. So clearly the appetite to make this all very efficient through the packaging and other types of innovations that are coming down the pipe is hugely exciting and something that we are really looking forward to. So if you go on to the next slide, Ravi. So here I kind of talked through some of the differences these different stages bring in terms of challenges. And herein also lies an opportunity for the types of packaging and test innovations that are coming down the pipe. The first section, as we talked about, is usually a storage challenge. And then the training piece deals with how do you efficiently connect these scale-up training accelerators through the network. And then as we get into the deployment phase, both the training and the inference also have differences in terms of compute and memory focused challenges. So as you look through this picture, you kind of get a sense of some stages in the pipeline need a lot more capabilities on the network, and some stages in the pipeline need different mixing and matching of compute and memory. So as we try and solve this all in a more efficient manner, if you look forward, uh, the speed of innovation that we need in the space is pretty quick, right? Like the machine learning algorithms and AI algorithms, they evolve at a rapid rate. And so we need to be pretty flexible and efficient in terms of innovating here. And that is where some of the upcoming technologies and around packaging, the new chiplets, and those kinds of things that are down the horizon, we certainly do believe that they will rapidly help us in terms of increasing the speed of innovation with a greater degree of flexibility. And we're really excited by the work that the community is doing in the space. So moving to the next slide. Even within machine learning, one of the things that I did want to get across is there is a difference in terms of the types of workloads that we deal with. So for instance, in this particular slide, we're talking about the different types of workloads and the relative importance they presented to us maybe a year or two ago, right? So clearly, ranking and recommendation is of paramount importance for us. This is around how we recommend to users what are the key workloads, what are the key things that the user may be interested when interacting with some of the Facebook properties that Ravi shared. Clearly, computer vision and natural language processing, they are increasingly more important as we work through some of the services that we offer. Um, but the main point for the packaging and test community is this is not necessarily always a one size fits all. And even here, some level of flexibility in terms of how we are able to adapt the compute, storage, and memory hierarchies is going to be helpful for us as we move forward through the next 5 years. So hopefully this gave a good sense of the growth as well as the need to innovate and be flexible as we try and address the growing demand that these applications face on us. So we're really excited by the work that this community is doing to enable these types of end user applications. So in this phase, I'm going to be talking about, so you can think of what I just covered as one dimension. On the second dimension, I'm going to be talking about how we are thinking of this from a hardware and system implications. So as Ravi shared in the earlier slide, we have a range of properties, right, which are doing general purpose computing and through which they're serving our users. Now we have these new set of richer workloads like AI, ML, video that have all required some level of accelerators and unique infrastructure that are now fitting into general purpose compute. So we'll talk about how we deal with balance both of these from a system and an infrastructure level that the packaging and test community needs to be aware of going forward. So moving on to the next slide, Ravi. Thank you. So in this slide, I'm kind of talking through how does the accelerator fit into, for example, our server or rack infrastructure. So for a second, if you completely ignore the picture on the right side, the boxes which say GPV2, the section on the left is kind of how our classic server infrastructure would look like, right? You have multiple CPUs, and these CPUs are connected to the network, and that's how our general purpose infrastructure is. This continues to be a significant piece of our infrastructure now and going forward. So the first message I have for the packaging and test community is, as we go through these new packaging and test innovations, and we are coming up with these new accelerators for these new workloads like AI, ML, video, they do need to plug into existing data center and edge server platforms. So already there is a level of constraint in terms of the types of platforms into which they need to fit into in terms of how they operate going forward. And this is something that will be true for example, AI, ML, as well as for video from an accelerator use case standpoint. So now the picture on the right is kind of how Facebook has deployed some of the accelerators over the past 2 years, be it whether AI inference or whether it is video, where we have a number of accelerators which are around, we'll talk about this in a little bit, around 10 to 20 watts that kind of fit into an M.2 or a dual M.2 form factors. And many of these blue boxes, as you can see, they are connected into via a PCIe switch, and they all go into a card, which we call GPv2 or Glacier Point V2. So one of the implications is this entire GPv2 box, it kind of has a similar thermal and power profile, or similar to the picture on the left, which is called Twin Lake. So this is an example of how we are adapting some of these accelerators into our existing general purpose server infrastructure. So moving forward, so then the next level of consideration is, what is the type of form factor that we have these new accelerators that come into play? So as you can see, one of the other considerations that we have is, as we have these new workloads, can these new workloads and accelerators, can they leverage existing standards around flash, thermal, mechanical, so that we don't have to uh, invent unique things for these specific uh, use cases, right? So for instance, one of the use cases that we have deploys using an M.2 module, which is around 10 to 14 watts at the module level, and uses unpackaged DRAM, LPDDR, as well as the ASIC. So all of that goes into the card. So one of the main messages I do want to have for this community is, clearly, as we do AI training and things, we do embrace higher TDP and such, and then we continue to work with pretty large scale devices. But we also innovate a lot in the lower end, so to speak, right, where it is a 10 to 15 watt envelope, even for a hyperscale data center. And these are areas where real estate is at a premium, as you can see from this card and form factor. So the amount of efficiency we can bring per unit area into these form factor, that is also an area that's hugely interesting to us. Moving on to the next slide. And the second point I want to make is, these form factors are things that also continue to evolve quickly. As I mentioned, the workloads are pretty demanding, and they change a lot in areas like AI, ML. So for instance, here we are showing a next gen module, which is a dual M.2 module, which leverages what I showed in the prior slide, but it increases both the PCIe bandwidth into the server host, as well as increases the thermal envelope of the accelerator up to 25 watts. And this enables us to run more complex models on these ASICs. But they do present a level of backward compatibility with the prior generation. So the main point here is, they need to stay close with the community, such as yourself, was working on the packaging and test space, and then make sure that we are able to match the fast growing workloads to the form factors and maintain some level of backward compatibility where possible, in order to drive efficiencies in terms of how they get deployed in the data center. The next level consideration I wanted to talk through is how we integrate these accelerators into our server and rack infrastructure, right? So this picture, if you look at it, on the left side was the module that we said. And then this module gets integrated into what is called a carrier card, where you can mix and match up to 12 modules of these into a Glacier Point carrier card. And these go into what we call a sled. So the sled, for example, can have 4 CPUs during general purpose compute, or it can have 2 CPU cards and 2 carrier cards, which have these up to 12 accelerator modules that all get mixed into the sled, and they have a shared NIC through which they connect to the to the top of rack. So this is the configuration that, for example, in this generation, that was of relevance to us. So it's very important for us to work very closely with the packaging and test community in terms of trying to figure out how we can optimize it for this environment, right? So we can drive the right trade-offs in terms of power, performance, cost, so that it's not something we over or under designed for. Um, so for instance, if the development consideration was just taking into account the constraints of a single M.2 module and not taking into account the carrier, sled, and rack level deployment considerations that we have, it wouldn't necessarily be a pretty optimal design. So that's where we had to come together and work closely with the community and the partners in terms of making these happen. The other point I would make from a test standpoint is many of these workloads are moving things off from general purpose compute, where things like early life failures, degradation, a lot of those kinds of things have been well understood and tested. As we come up with these new unique architectures for these key workloads, the same promises that we make to the applications in terms of data integrity as well as reliability, they need to carry forward. Okay, so moving on to the next slide. So it's very clear that the form factors will continue to evolve as the workload moves. So for instance, we already know that the M.2 and the dual M.2 form factors will not scale for the future, because when we look further out, we see the evolution of storage devices continuing to happen with things like the E1.S types of form factors. There are new I/O transitions happening around things like PCIe Gen 5. The models are getting more and more complex from an AI ML standpoint, where we need to, the minimum size could be as high as 30 watts for some things like AI inference. So we are continuing to work with the community through the Open Compute Consortium in terms of trying to drive standardization of these form factors. And clearly the packaging and test aspects of it are critical in terms of how we influence the form factor direction going forward. So as an example of the importance of the packaging and die sizes and how it impacts our form factor, this particular slide shows a simulation of Facebook's Yosemite V3 system. And when we had a 20-watt bare ASIC and its implications based on die size. So as you can see, going from the left to the right, when the die size continues to scale, there is a significant need to drop the temperature, right, from an ASIC standpoint. And that kind of creates unique requirements for us in terms of how we deal with this relative to the general purpose server infrastructure. So these are the types of things which the form factor needs to now compensate for, as well as the thermal and the rack level cooling that we have to take into account. So clearly, as we look forward, as the community is thinking about different ways of innovation around packaging, whether it is chiplet integration, vertical stacking, whatever those methodologies are, we need to closely work not just at the module level, but also at the system and rack level integration to find the right level of optimization for these workloads. So the key takeaways are from this section are clearly we have a significant appetite for the type of innovations that are being pursued in the packaging and test space. I would encourage the community to also think at innovating in a fixed real estate and power budget, not assume a data center implies that there is a large power budget to play with. As I mentioned, many of our accelerators around AI inference and video continue to operate at the lower end of the thermal envelope, like 15 watt, 30 watt, that kind of a space. So let's drive innovation in that space and not just focus on the high end. And clearly the test innovation needs to preserve the data integrity, the reliability that we've come to expect of server class CPUs as we pursue these new types of accelerators. early co-engineering and co-development around things like packaging and die design is critical for us as we look to operate, influence our form factors and fit into our rack and chassis level infrastructures. And this is something that will continuously change based on workload requirement and how the adjacencies like the storage market continues to evolve. So this is an area where we need to closely collaborate with the community. And then the last one I mentioned, uh, it is good that we are pursuing a number of new innovations in terms of packaging, but they do need to preserve the data integrity promise that we get from the older generations around monolithic devices or traditional class devices. And that is something that we do need to pay attention to because these workloads are mission critical. And so they do need to provide a certain level of reliability that we have come to expect from server class applications. Uh, that kind of concludes this particular section. So we will transition, I think, after a Q&A to the networking sections. So I'll hand it off to Ira for Q&A.
Okay, great. So a few questions, and obviously, you know, we're not looking for trade secrets or family jewels, but in terms of cooling capacity, since the architecture you showed is air-based and most of your data centers are air-based, is there like a difference between the cooling capacity of a sled at the bottom of the rack versus you know, or a tray at the bottom of the rack versus a tray at the top of the rack, or is you know, is there a wide variation there that has to be accounted for?
At a high level, I would say that the servers that we end up deploying within a rack all operate at a similar level of thermal and power envelopes.
Okay, got it. So either the envelope has to be wide enough or you're able to get the cooling uniformly enough across the rack. And related to that is a question, you know, we know other people in the market have done water cooling of AI devices. Is water cooling, let's say, or liquid cooling, a bright line that you are deliberately choosing not to cross, or will it be crossed when the numbers make sense? I mean, some people may start from, no, we're just going to always use air. Is there a boundary condition related to that? I mean, I'm sure you've looked at it, so.
Yeah, I mean, we definitely look at all types of technologies across the types of problems that we need to solve and try and find what is the right optimization point for us across the types of services we need to do. I think and I think we continue to look at all technologies for the future.
Got it. Okay, got it. And then with regards to memory and logic, you know, you showed your modules. I mean, how close do they really need to be? Or can you comment on the performance difference depending upon the different levels of integration, i.e. having them on, you know, certainly having them on the motherboard in different places has a different level of performance than having them integrated in package. I mean, and does it make a difference for your kind of workloads?
Yeah, I think
memory.
Is the question on, we talked about these ASICs, is the question about having multiple ASICs versus having them integrated? Can you clarify?
So the question is, you know, when you look into the future, do you see a specific need or specific requirement in terms of the level of memory integration? So there are people who may co-package a high bandwidth memory with a custom ASIC to really closely couple them, or there's, you know, at least the diagrams you were showing, you know, the memory might be somewhere else on the module or even all the way back to the CPU memory. So for the type of workload you're looking at, is there a general direction you think that needs to go?
Yeah, I think clearly, like if you look at some of the training platforms, which I did not show in the slide deck, if we look at some of the training platforms that we have disclosed at Open Compute and such, we do have larger accelerators like GPUs, which have like co-packaged memory for HBM that we use. So in this particular case, our desire or need was more for capacity and not as much for bandwidth. And so in this case, and also the fact that we wanted to be in the thermal envelope of around 15 to 20 watts as it maps into this thing, which is not very amenable to co-packaging things like HBM. So it was a combination of the workload need and the form factor to fit into our server infrastructure, which led us towards this direction.
Okay, got it. There was a question related to the chart you were showing that as the package size increased, the power decreased, which intuitively doesn't feel right, because normally the bigger the die size, the more power consumption, assuming the same process node. So you had the chart with the different sizes, and you showed the power went down as the size went up.
So the y-axis was not power, the y-axis was temperature for the ASIC and what we had to do in terms of thermal capabilities. And so to fit it into that envelope that we had.
Got it. Okay, got it. So you showed a specific question, the ASIC temperature in one of your graphs with the temperature impact graph. Was that the junction case or junction or the case or something else, if you recall?
Junction. Yeah.
Junction, okay, got it. Okay, and then let's do, I think, one more. Do you think power, well, you're using optical interconnect fairly heavily, but as people are moving the optical transceivers and there's discussion, the heterogeneous integration environment of putting the actual optical transceiver in the package with a device, do you see power consumption shift occurring with higher levels of photonic integration?
That would be an excellent question for Ravi for the second part.
Okay. Okay, so
I'll hold on that one.
Okay, got it. Okay, and then okay. Actually, and this is a design question. When you look at the integration need, because you're looking at modules, carriers, sleds, and racks, what kind of challenges do you foresee from co-design EDA point of view? Because you're designing at multiple levels, and you probably have different criteria at the data center level and at the device level. So do you see any co-design or EDA challenges that are open that you need solutions for as you're doing this work?
Yeah, maybe taking those two things a little bit separately. From a code design standpoint, absolutely, right? As I mentioned, these are things that continue to change. There is a level of hardware software co-design that happens for the application, and then there is form factor and packaging and other things that need to come together also. And then these things rapidly change for these types of workloads than traditional workloads. And so there is definitely a lot of code design that needs to happen, which is what we try and work through things like the open compute. We participate in consortiums like for example, CXL, where we try and influence the direction so that we can still stay off package, but get the benefits of lower latency, cache coherency, and those kinds of things with on the same PCIe hardware infrastructure. So absolutely, from a hardware co-design standpoint, we see a lot of need, and we actively are involved there. In terms of EDA design challenges, I mean, I think since we are talking about this that's not something that I have a significant perspective on at this time.
Okay, great, thank you.
So Ira, shall we move on?
Yes, great.
Thanks, Bharath, and thanks for the audience for asking great questions. So I know there was one question related to photonics and getting close to the ASIC. So as Bharath shared our overall Facebook system level architecture, and besides rack, there is another thing which is very important in our hardware ecosystem, which is network and power related to network. As Bharath shared that, our AI ML workload is increasing in our data center, and machine to machine traffic is growing rapidly. And as you can see in the pie chart, which is shown on the right, our network power consumption is proportionally going higher in our data center power budget. And in power allocation in data center is typically being constrained. And if networking takes a big portion of that power, which means less power will be available for some of the important function of compute and storage. So power has become one of the biggest emerging challenges, both for Facebook as well as for other hyperscaler. So this is an example of a typical networking switch. This is a top of the rack switch with 100 gig SerDes, where you can see 50% of power is being consumed by switching and about 90% by optical link. But if you look at this chart carefully, there is about 20% of power is being consumed by I/O, between switch I/O and optical I/O. So moving them closer can eliminate this 20% power consumption or reduce it, and potentially up to 50% with saving from retimer goes up as speeds of electronics go up. So this is an evolution of some of the optical interconnect, where we started from pluggable optics, and from pluggable optics to we moved on to the onboard optics, and then from onboard optics moving into the co-package optics, where bringing an optical interconnect or optical module next to the ASIC. And the idea is we will have shorter electrical channel, and that will drive less SerDes power. And based on our estimation and some of the work which is being done in the industry, this overall configuration will provide lower power and of the order of about 400 watt power reduction compared to conventional system. So Facebook is driving this co-package optics works, and try to build an open ecosystem and foster innovation where we can have multiple companies can play a pivotal role. And we have a JDF in collaboration with Microsoft, and both in this, as part of this JDF with Microsoft, we have published architectural guidance document for co-package optics. And Facebook is also driving some of the standard development of standard work at OIF, which is Optical Internet Working Forum, and as well as at IEEE. So this is a schematic of a co-package system, which you can see on the top has a switch package in the center and 8 optical module surrounded the switch package. And both switch and optical package will be mounted on a common substrate. And I want to highlight some of the challenges to make such a package in future, and especially for this community, which can appreciate some of the challenges we will see here. So this will be the largest package which in concept has ever built, and this will be about 2x the size of the most commonly available accelerator or high performance computing package which is out there. So when you are talking about mounting a switch package and 8 of the optical module on a common substrate here, so the substrate will be huge. And actually, as a matter of fact, there is no organic substrate which exists today which can meet some of the requirement which is laid out. So there is a lot of work which is happening in the industry where companies are working with the substrate vendor and trying to see how far we can push. So now when you have such a large package, then it comes with some of the other challenges like thermal management. This co-package optics package have different packages. So the question is whether you will have a one lid or whether each package will have its own lid. And if that's the case, how would you come up with a heat sink which can tolerate different heights in the packaging? And now, since it's a very large package, there will be a lot of warpage related issues this package has to address. And on the right hand side on this co-package optics, we have shown this optical module, and for optical module we are looking into some of the advanced packaging where multi-die integration, either using 2.5D silicon interposer or 3D die stacking. And for this switch package, which is mounted onto a substrate, industry is exploring different business model, because the question is if this will be done in an open ecosystem. So whether the switch will come on a substrate and somebody else will integrate the optical module, or it will be a vertically integrated system where one company does everything. So this slide shows some of the concept which industry has demonstrated so far, starting from Cisco, Intel, and Rockley and Renovus. So there is industry momentum is building, but still it's fragmented. As you can see, each solution looks different from other. So there is a lot of standard needs to be developed, and industry needs to come together where we can have a common or at least a co-package optics which will meet different types of workload and the power envelope. Now I would like to shift a little bit and as continue our journey to develop an open ecosystem, whether like for M.2 card or co-package optics. We are looking into addressing challenges related to slowing of Moore's law by enabling heterogeneous integration. And we are actively driving development of chiplet marketplace in ODSA, which is a OCP workstream. As you know, most of the chiplet product which is out there are vertically integrated and has a very close ecosystem. So ODSA is focusing on developing an open ecosystem in around IO disaggregation, core disaggregation, and system integration of chiplet. To foster this further, ODSA is organizing a chiplet business enablement workshop, and this workshop will be focusing on what is the current state of the art chiplets and identify gaps and some of the challenges that exist in a value chain when a hypothetical product, which is shown on the right hand side of this slide, which is like Mara chiplet product, when it moves into the ecosystem, what are some of the challenges each of the vendor sees. And we have invited industry experts from different part of these value chain, starting from end customer, which are all the top 3 or 4 hyperscalers, foundries and IDM, leading OSATs. We have all the leading IP and design houses and system integrator, which typically today, again, I don't want to list names, but there are a lot of details shared in this link, which is shown here, where you can go and register. So this will be a workshop which will happen on March 12th. Now, I want to, in my last slide, leave you with this thought. If you want to go fast, go alone, and we believe if you want to go further, go together. Thank you.
Great. Thank you, Ravi. One question that comes into mind, and I'm sure the audience will chime in with lots of other questions, but if you need a really large package that's bigger than available laminates, have you investigated or considered maybe using panel level packaging? Not sure what the technical requirements are, but certainly you can build much larger structures than traditional laminates that way.
So my understanding of panel level packaging is when you are integrating multiple die or chiplets, rather than using wafer level, you use panel level, and that I think gives you scaling. But at least in this generation, the thought process of co-package optics, at least Gen 1, is we are looking into mounting optical module, which is already consists of several die, and then we are looking into mounting either a switch package or a switch die. So we are disaggregating between the two and using some kind of a XSR channel in the substrate to drive the power down. But down the road, when we will have, say, optical chiplet and switch come as a chiplet, then can we look into panel level packaging to integrate everything? Maybe.
Okay, got it. And it makes sense. And then a question in particular, at least initially, or what's the thinking on the light source, whether it'll be an external laser or integrated into the chiplet, the optical chiplet?
So there are different trains of thought in the industry right now. If you look at some companies have more integrated laser as part of their SoC, and others are looking at more external lasers. So different companies are coming up with different solutions right now.
Okay, got it. And is one of the challenges still getting enough? Obviously you have multiple transceivers at least sketched out in the design, but are you still fighting a restriction on how close the transceiver can get to the SoC due to heat generation?
So thermal is playing a big role, but distance between, if the question is distance between the optical module and to the switch package, is it distance is driven by the thermal challenges? Did I get it right?
Yes, correct.
So actually, that is more driven by right now, electrical channel loss, which we have between the two packages. Rather than thermal, but definitely thermal will play a big role. That's where I'm saying thermal budget management of whether you will have individual package have their own lid versus you have a one big lid which will have across all those packages. And would you have a bare die in the center for a switch and then a lid for the optical module? All of these things needs to be worked out.
Got it. Okay. Wow, the questions are coming in crazy. I mean, one question is, how big is the package roughly that you're envisioning? You show in your slide, and the question is, how big of a concern is warpage? I know you mentioned it, but can you give us you're thinking 150 by 100? I mean, rough numbers.
I'll just share some of the number which is shared in the OIF, which is
Right.
a open forum, and actually apparently there was one presentation from TE today. So industry is looking at greater than 100 by 100 millimeter packages, and as large as beyond what a substrate manufacturer can make. So yeah, I'll just leave it there, and there is a lot of information out there.
Got it. Okay. Okay. Somebody was asking, was the substrate you showed for the optics module and the main package substrate are they the same? But I think the diagram you had a base substrate with the optics having a subsystem with a substrate in there too. Okay, so I think that's that one. I think they just need to look at that a little closer. Okay, and I'll ask this one. Does 1 dB of loss in a high-speed package signal multiplied by the number of packages in data center have a cost impact? So sort of maybe I'd flip this around and say, what's the value if you could eliminate a 1 dB loss in your high-speed package? I mean, are we talking, millions of dollars worth, or is it okay, that's maybe a 2%, sort of?
So as I shared in that pie chart about currently we consume 20% of power in our IO between switch IO and optical IO. So at the bare minimum, you are taking out that 20% of power consumption if you can move them as close as possible. And then there is some other benefit coming from the retimer, and the more efficient compute standpoint. So to answer that question, based on our conservative estimate, we are roughly looking at around 400 watt power saving if we enable a co-package optics.
Okay, got it. And then I'm assuming people could do the math, and I'm not going to talk about your data centers, but if you have a 50 megawatt data center and you save 2%, 20%, that's 10 megawatts. And if you use $1 per megawatt per year, that's $10 million a year. I mean, they can do some math along those lines. I mean, but those are sort of the numbers I've seen. So got it. Okay. And the integrated laser using silicon photonics, are today, or are there some capability differences between maybe an off-chip laser in terms of power and wavelengths? Or have they caught up pretty much to what's available as an external source?
So I know at least there is one company which look at SOC type of laser waveguide, and then most of the industry is looking at external laser. So in one case, it's the availability of the IP, because not every, if you look at leading optical vendor, there are not that many vendors who can do a optical wavelight or a SOC type of. So I think in the end, it's overall system level optimization. So external laser is the most commonly used today, and that's the more. If you look at some of the proof of concept which I have shown in the coming from the industry, most of them are looking into the external laser.
Okay, got it. Okay, and then do you, and this is maybe a leading question, but do you expect multi-wavelength signaling to be used between chips? I mean, so sort of the approach you were showing was getting the SoC chip and the ODE interface as close as possible to reduce power consumption. But let's talk, let's say on a board, would you see a crossover point where you might actually do optical interconnect between ICs on the same board or same sled versus across the data center?
So definitely for this generation, the body of work which I shared, that's not the intent here, but that's where I see industry is heading, where people are looking at optical interconnect for memory disaggregation, or maybe between accelerator to accelerator communication. And there is, in fact, there was a talk in HIR today by DARPA, and as well as I think a professor from Stanford. So again, industry is looking into those things.
Great. Yeah. Okay, well, it looks like we've tackled all the questions. So thank you, Ravi. Thank you, Bharath. Want to thank you for an excellent presentation and sharing, where you see things going. And I hope that people will investigate some of the open activities to try to help find solutions to some of the challenges, because as we know, the consumption of data and the workloads are continuing to go up. And I think certainly for both economical and environmental reasons, it's all in our best interest to reduce the footprint of our growing appetite. So thank you both. So I wanted to once again thank our speakers and remind everybody that we are looking forward to the next two Semiconductor Industry Speaker Series presentations. John Park from Cadence Design Systems on March 10th, and Tom Green from TJ Green Associates on March 24th. The webinars start at 11:30 a.m. Pacific time. And if you're interested in speaking at a future Semiconductor Industry Speaker Series, please let myself know or Dave Town, and we look forward to having you join us then. And once again, I'd like to thank everybody for participating in today's event, and I will wish you all a good day. Thank you.